So welcome to this tutorial session. Now that the base setup is done, so the goal of this tutorial will be to introduce you with advanced machine learning concept as implemented in Scikit-learn, and we will especially focus on making basic machine learning algorithm from Scikit-learn scale to largish data set. It's not big data because we won't address like Google size data set, but stuff that might not fit in the memory trivially, or stuff that will need more than one machine to run. So during this tutorial, we will mostly use the laptops that we have here. So the data sets are even smaller than what you could do if you had more machines. So a couple of words about myself. So I'm Olivier Grisel. I'm a regular contributor to Scikit-learn. Jack, who is moving around, is another core contributor of Scikit-learn. So Scikit-learn is a library for machine learning that started a couple of years ago, and it's getting more interest because machine learning in general is getting more interesting. So myself, I'm interested in natural language processing, a bit of computer vision, predictive modeling in general. And I'm recently tried to investigate with how to leverage cloud computing resources to make all of those run better. And I will be starting my own machine learning consulting business. So if you're interested in a project, you can go to this webpage, orgrisel.com. So the outline of this tutorial will be the following. We will start with one of the most fundamental concepts of machine learning, at least one method that everybody should know about and apply on a day-to-day basis when dealing with machine learning issues, namely how to do proper model selection and assessment of the quality of the statistical models that we fit on the data. One of the motivation for dealing with this during this tutorial is that this specific kind of task that we do on a regular basis in machine learning are almost all of the time embarrassingly parallel, and so they are amenable to scaling on a computer cluster using IPython parallel. So we will have in the second section an introduction to IPython parallel and an application to the topic of the first section, which is model selection. Then we will have a break at some point. I don't know. It will be at 2:50, something like this. And then we will move on to text feature extraction and classification. So it's one of the main application areas of machine learning. It's how to process unstructured data such as text. And we will focus on classification, which is a simple task to illustrate the issue. So text classification, in real life, it can be like spam classification, fraud detection, or comment spam or mail spam and whatever. It can also be a sentiment analysis when you are trying to see on social networks whether users speaking about a specific topic are speaking about it positively or negatively, to know who are the influencers on a specific brand, for instance, and identify people you should focus on converting to speaking positively about your product, for instance. So those are the kind of application of text classification. Then, if we have time, we will move to how to scale text classification to larger data sets. And if we are able to scale, we can do two kinds of things. The first one is how to do online learning or out-of-core learning, which means how to fit a model to a data set that doesn't fit in the main memory of a single computer. So how to stream the data into the model and to make it fit to learn incrementally and then have a final model that is a summary of a complete data set that doesn't fit in memory. And the second part will be how to do this in parallel on several machines, on several computers, possibly distributed on the cluster. So before diving into the actual tutorial, the organizers of PyCon are looking for volunteers. So tonight there will be a swag bagging session. So if you can help fill 10 bags, it's good. Otherwise, they need people for the registration desk. I think tomorrow morning will be very important. And so if you are interested in volunteering, you can go to the bit.ly/PyCon volunteering status page. And finally, there will also be, I'm sorry, yep. If you go to the tutorial setup page, notebook, at the end there is a link for the tutorial survey. So it's a SurveyMonkey page. So if I forget to ask you to fill it at the end, please do it tomorrow or when you think about it in the coming days. All right, so everybody is fine with the setup? Okay, so let's open the first notebook, which is called Model Selection and Assessment. Actually, maybe before going into this one, let's get familiar with the notebook itself. So instead, click on the new notebook page here, and we will see how it works. So the notebook is kind of a shell where you can write both documentation and see the output of the execution of the code you put in line. So whenever you put some Python instruction, for instance, print something here, you can execute it by pressing Shift-Enter, and it will move to the next cell. And if it's the last cell, it will insert automatically a new code cell at the end. So in the notebook, you can define variable as a regular Python program, and then print the content of variable. It's just a Python process running in the background. When you go back here, you can change the existing code and re-execute this guy several times by pressing Control-Enter. And in this case, it won't move to the next one. So this is very interesting to monitor the state of a process running in the background. So it's Control-Enter. And you can see that the state of my notebook has changed because now my A variable is 13 here. You can also, if you're interested in tweaking something, you can copy and paste a cell by pressing Control-M-C, Control-M-V, and it will duplicate the cell, and you can actually put it somewhere else, Control-M-V here, and then you can edit it and change it. If you want to get rid of it, you can press Control-M-X or D to cut or delete. You might want to show on the help menu. Yeah, and then there is the okay. All of those operations you can perform them using the menu, and then you can get the list of the shortcuts by pressing Control-M-H for help. And here you have all of them. Or from the help menu. What? Or from the help menu. Help menu? Help keyboard shortcut. Oh yeah, I missed it. Okay. Okay, so the most important are the Shift-Enter and Control-Enter to either run in place or to move on to the next cell. Actually, it's the opposite. Okay, so now we can close this tab and go back to the first one, which is model selection and assessment. So in this first section, we will see different kinds of of ways to evaluate the quality of machine learning model. And especially, we will try to detect one of the bad situation where we can end up when learning a machine learning algorithm, which is called overfitting. So overfitting is when a machine learning algorithm has learned by heart what is seen in the past and is not able to generalize to unseen data in the future. So this is a trap, and the best way to detect whether or not we are in this trap is to use what we call cross-validation. So we will see how to do this with cross-validation. Once we know how to do cross-validation, we can extend this to do hyperparameters tuning, which is how to automatically tweak the knobs of the machine learning model, like the hyperparameters, the constructor parameters of scikit-learn models, by using what we call grid search, which is basically trying many different values for those parameters, learning the models on the data, and then validate it against new data and measure the performance and selecting the best model according to this cross-validation performance evaluation. Once we have this, we can also evaluate the quality of the model and especially try to see how we fit in the bias variance trade-off by plotting what we call learning curves. And finally, we will see that we should always do this on a specific subselection of the data set, which is called the development data, and try to get some held out data for the final evaluation at the end. So let's start. So before starting with the actual execution, we need to run this cell to configure the plots and import a couple of utilities. So please run it using Shift Enter, and then it will move the cursor to the next one. If you get an error message, raise your hand. Okay, so to illustrate those concepts, we will need a data set. So as we did this morning in Jake's session, we will use the digit data set that comes by default in the Scikit-learn source code, so it's easy, you don't need to download anything. So to get this data set, you can use the scikit-learn.datasets package and import the load digits function. When you import this guy, you have a digits object that has a description, so we can print it. And you can see that it's a data set about optical character recognition, where all the characters in the data set are digits from 0 to 9. And there are small images with 8 by 8 pixels. So if you put all those 8 by 8 pixels on a line, on a row in a matrix, you will have 64 pixels per image. And as we have 5,000 such images, we say that we have 5,620 samples and 64 features. So hopefully you're all familiar with this way of treating the data, this vocabulary. This is the standard vocabulary for machine learning in general and in scikit-learn in particular. So let's load the data set into two variables. So the first variable will be x, which will be a two-dimensional matrix with the actual pixel data. And y will be a one-dimensional variable with the integer labels for each of these pictures. So if we execute this, we can see that we can plot the shape attribute of the NumPy array x, and the same for y. And we can see that the data shape is this, and the target is just one-dimensional with the same number of samples as the first dimension. So here you can see that we have only less than 2,000 of the pictures of the images, because it's just a subset of the actual data set that is published on the internet. We can also use the NumPy function unique to get all the different values of the Y array. And we can see that there are 10 classes for the 10 digits. And those classes are represented by integers to be memory efficient. So we don't have strings in Scikit-learn. Most of the time we directly process numeric values to avoid storing strings in memory to reduce the memory usage and make the computation faster, basically. So I could insert a new cell here and have a look at what's the content of the Y variable. And you can see that the data set has been a bit shuffled. I'm not sure, so I will move a bit in the middle. Actually, it hasn't been shuffled, so it's just a repetition of pictures from all those values concatenated one after the other. So the dimension of the data is called the samples for the first dimension and the features for the second dimension. So the samples are the pictures, and the features in this case are the pixel values. Once we have this data set loaded in memory, we can also use matplotlib to plot the actual content. In this case, we know that those are pictures. So each individual row in the X matrix will be 64 pixels. So we can reshape it to a picture with 8 by 8 pixel and use the imshow function of matplotlib to display it. So if we do this, it will iterate over the first 5 samples in the data set. And it will display the true class in the title using the Y vector, and use the imshow function to see the pixel value in a visual representation. So we used interpolation nearest here to disable the interpolation features of matplotlib to see the raw signal that we have in the data set. So here we can see that this is a 5. It's quite obvious. A 0, a 6, another 0, and a couple of zeros actually. So once you have a data set loaded in memory, the first stuff that you could do when doing classification in Scikit-learn is to try to represent the structure, the distribution of the data. And as we are human people, we try to see stuff in 2 or 3 dimensions. So we'll try to reduce the data into to project it into a 2-dimensional space, and then do a scatter plot into this space to see the actual distribution of the data. To do this, we can use randomized PCA, which is an approximate principal component analysis method that is provided by default in Scikit-learn, which is very scalable. So you should always use this one when you want to do visualization on large data sets. So we can import it from the decomposition package of Scikit-learn, and then run it by building an instance with the n components parameter set to 2, because we want to project the data into 2 dimensions, the first 2 principal components of the data. And then we will call the fit transform method on the data, and that will extract the structure of the data and then project it into this space at once. And the resulting variable will be xPCA and should be 2-dimensional space. So you can see that it's quite fast. And we still have the same number of samples in the transformed data set, xPCA. But now, instead of 64 features, we just have 2 dimensions. And those are the projections of the 64 features onto the first 2 dimensions. So once we have this, we can run a scatter plot using matplotlib by plotting those 2 dimensions. Here you can see 0 here and 1 here. And we will use different colors for the different values of Y here. So we will select the subset of xPCA for all the possible value of Y. And we will use a different color here and plot a legend with the match between the integer values and the colors. So let me toggle this. put it full screen. Okay. So, yes?
Depending on the version they have, some people are going to get an exception with label equals I. So put str of I around str.
Okay.
And that's what they will try to treat it as string.
Okay.
Depending on the version, so that'll avoid it.
Good catch. So I can re-execute it, I should get the same thing. So str of y in the label if you get an exception. So here you can see the data set that has been projected down to this two-dimensional space. What we can see is that we can observe that it's not just pure noise, it has some structure. And in particular, you can see that the blue elements, I know that they are here because there are two blues, but they are the zeros here. They are quite well isolated from the others because the zero has a hole in the middle, which is quite specific to it. And so if you compute the distances between in pixel by computing the pairwise distances and summing those, you can see that they are quite different from the others. You can see that the closest digit to the zeros are the 6 here, the black, because you can say that the at least almost whole of the left-hand side of the digit is very similar to a 0. So down to this two-dimensional space, it has been projected to a location that is close to it. You can also observe that the 3 is between the 2 and the 9 because they share some elements and so on. So it kind of makes sense to see the data like this. And you can see that some of the numbers are quite mixed together. So if we were to try to fit a machine learning model in this two-dimensional space, it would be very hard to separate those guys. To separate the zeros from the others, you would just have to draw a line here. It would be quite easy. But for those guys, it would be much harder. So we say that we did lose too much information when projecting to this two-dimensional space. But for us human, it's the best way we can have a quick look at the actual structure of the data. So let's move on to the actual concept of overfitting. So let's try to fit a machine learning model on this data set. So the first model we will use is SVC from the SVM package. SVC stands for Support Vector Classifier, and it's a nonlinear classifier because it uses a kernel which by default is the RBF kernel of the support vector machines. To know what are the default parameters of a model in Scikit-learn, what you can do is create an instance of this class and just print it, and you will see all the different default values for the parameters of this class. So in this case, you can see that the kernel is RBF. So it's kind of a complex model that will be able to fit the data. So we call this model, we call the fit function of this model on the data, x and y. By default, fit in Scikit-learn returns the self, the same instance, so that you can chain a call with the result. And here we are computing the score of the model on the same data set, so on x and y. And you can see that we have a perfect score of 1. So the score is the rate of correct classification in this case. So the ratio of correct classification. So in this case, we know that the model was capable of perfectly memorizing the data set. But as we have computed the score on the same data set as the data that we use for training, we have no idea whether this model will be able to predict good stuff on new data set. So to make this possible to evaluate, we have to split our data set into a training set and a test set. So by default in Scikit-learn, you have this utility function from the cross-validation package that will split x and y according to some ratio. So we will hold out 1/4 of the data for the test data, and keep all of the remaining data points for the training set. And so we have X-train and X-test, Y-train and Y-test. And we can check the shapes of those NumPy arrays and see that the train data and the target train data, they have the same first dimension because they have the same number of samples. And the test set is much smaller because you only have less than 500 samples for testing in this case. So now that we have split the data into a training set and a test set, we can retrain a new model, which is called SVC, only on the trained data, and then compute again the score on the trained score, on the trained data, just to check that we are still able to memorize the data set perfectly. But now we can also compute the test score on the unseen data, stuff that was not seen during training, and we can see that in this case we are making less than 50% correct predictions. So clearly the model is not good, and because there is a big gap between trained quality, the score on the trained data and the score on the test data, we say that the model is overfitting because it has learned stuff by heart and is not able to generalize. There is a big gap between the two. If the model was not able to achieve 100% performance on the trained data, we would be in another regime which will be called underfitting. It's a case where the model is not powerful enough to model the data. So we can try, so in this case we use the default parameters. We can try with alternative values for the parameters. For instance, for the kernel, sorry. Okay, so we use the same kernel, but we use different value for the C and gamma parameters and train another model. In this case, we still get a perfect prediction on the training set, and on the test set, we get almost perfect predictions. So those values for C and gamma, I knew them because I did some cross-validation and grid search. So here is how to do it. In this case, I did a single split. So the value that I get for the score here will change quite a bit if I did a different split by changing the random state here. I can compute another split here by changing the random state. It's a random generator seed. And then compute again here the values. And you can see that the test score has changed quite a bit. Not much, but a bit. So we are not sure. This value, the score value, depends a lot on the random split. So to make it less dependent on the randomness of the split, we can iterate this process several times and compute the average of the score and the standard deviation or the standard error of the mean of the score. So this process is called cross-validation. To do this in Scikit-learn, you can use shuffle split from the cross-validation module. It's an iterator that will generate train and test sample indices, and you can use those indices to slice the data set and to compute different value of the model by training on different train sets. So here I did only 3 iterations, 3 random splits. And you can see the first 10 indices of the test sample, of the train sample and the test samples. And each time I fit a new model, and each time I score the test, the same model on the test data. Yes? Sorry. I thought I caught them all. So depending on the version of Scikit-learn that you have, you might need to have n iterations here instead of n either. Sorry. So it has been changed in a recent version to make it more consistent with the other modules. Okay, so when you do this, you get the test score for the individual. The test score is here for the independent random splits, and you can compute the mean of those test score and get a better estimate on the actual generalization of the model. So instead of doing this by hand, by iterating over the cross-validation iterator manually, what you can do is use this cross-val score function from Scikit-learn that does it automatically for you. So you can create your own cross-validation mechanism custom if you want, or you can use a default one. And you can pass it to this cross-val score function as an argument here. And you can say that you want to run this in parallel on 2 CPUs by using njobs here. And here we did 10 iterations, so you will have to change this to n iterations equals 10 again. And you have the test scores for all the random splits. And you can see that, for instance, on this data, with this random seed, the last split was perfect, but it's just pure chance. So to summarize those 10 values, I can compute the mean and the standard error. To compute the standard error of the mean, you can use scipy stats sem function. So I will just define a display function here to print a summary. So the mean score of my model is 0.993 plus or minus 0.001. So it's quite precise in this case. Okay. So to check this, we will do a first exercise where you will have to compute 50 iterations of cross-validation using the same shuffle split cross-validation mechanism, but using 50 instead of 10. But to make this faster, you would just use 500 training samples and 500 test samples to make it faster. And to know how to do this, you should have a look at the doc string of this guy. Oops, sorry. Shouldn't. To see how to adjust the size of the training set and the test set. And then once you are able to do cross-validation, you should try on a model with those parameters by default. And if you know matplotlib, try to plot the validation errors using an histogram. Okay? So let's do this, and you can ignore the end of the exercise. So there is a couple of hints here. So on the API that you will need, you can import this guy. Actually, it's already imported, and then call the question mark at the end to see the docstring of the model. It's not a model of the function of the class. Here, and then you have the test size and train size parameters. Quick answer for this first exercise. So in the meantime, I switched my notebook to the solutions folder so that I can show you the solutions without typing them. So to compute the cross-validation with 50 iterations, so I will switch to n iterations instead. I create a new instance of the shuffle split class. I pass it the size of the total data set as I did previously. But now I will randomly subsample only 500 train and 500 test samples, and apply this cross-validation scheme to the by giving it to the cross-val score function on my model with the parameters that were given in the exercise instructions. And I will just display the score using my utility function for the standard error of the mean. So it takes a bit of time because it runs like 50 times. And at the end, I get 90% accuracy and a good precision on those 90%. So instead of just having the mean value plus the standard error of the mean, I can also plot an histogram using matplotlib. And I can also further use using SciPy Gaussian KDE, which is a kernel density estimator, to have an estimate to visualize a smooth estimate of the distribution of the validation score when I do many cross-validation steps like this. So it's more complicated than what I asked, but it gives you more value, more details. So you can see that the mean value here is 90%, as we found previously. The median is quite close, and the distribution is a bit skewed. It's almost Gaussian, but it's a bit skewed to the left because the 100% accuracy is a maximum value, so you cannot go more than 100%. So there is a bit of skewness here in the data, so it's almost Gaussian, but not exactly. So you can compute confidence interval and estimate the distribution this way. So it's very good to be able to do many iterations of cross-validation to have a fine-grained estimate of the actual validity of our model and to compute confidence interval if you are into statistics. And then you will be able to compare the intrinsic quality of this model on this specific data set with other models or other model parameters. So we could change the value of this guy here. For instance, if I use even stronger, higher value of gamma, I can rerun this. And you can see that the quality now is much worse. It's very bad, and I can estimate the distribution of the error. It's much wider at the same time. So in this case, I'm doing a 10-class classification problem. So if I predict a class randomly out of 10, I will have 10% accuracy. So this model, by doing 50% on average, is still better than predicting at random. But it's not that better. If I change to 0, 0, 1 here and rerun again, I will have a much better model, and the width of the spread of the test, the validation score, is much more narrow because they are almost perfect, all of them. So instead of tweaking the parameters manually like I did here and plotting the cross-validation score and selecting the best one, it's much easier to automate this using a script. So this is what we call model selection using grid search. So grid search is when you iterate over cross-validation for many different values of the parameters that you are trying to adjust. So in this case, I will just compute a loop here of a list of possible gammas. So I will take 10 possible values of gammas. I will put them on a log space here. I will split this cell into 2 cells. Okay. And display the value of gammas here. So I'm generating a NumPy array of 10 values of gammas on a logarithmically spaced scale. So it's starting with from 10 to the power -7 until 0, 1. For those 10 values of gammas, I can do cross-validation and compute the scores, the train and test scores for all of them, and store those into NumPy arrays, two-dimensional NumPy arrays. Once I have this, I can do plots of the scores, of the evolution of the scores according to the value of gamma. So for each individual cross-validation split, I did 10 different values of gamma, and I can see the 10 lines. So the green lines are the test errors, the validation errors, or the test scores actually, and the blue lines, they are the train errors. So you can see that the model can be into 3 different kind of regimes. In the middle, when gamma is optimal, you can see that the test score, which is the one that we are really interested in, is very good, and it's very close at the same time to the train score. On the right-hand side, for low-level values of gammas, you can see that both the training score and the test score are bad. They are almost random in this case. 10% is random for this problem. And in this regime, we say that the model is underfitting because it has not enough capacity to memorize the data set. The fact that we give a low value of gamma makes the model much too simple to be able to capture the structure of the data. When we give it more freedom by increasing the value of gamma, you can see that the blue line is going up until reaching the perfect model memorization. But if you give it too much freedom, it will learn the data set by heart perfectly and won't be able to generalize well to new unseen data. And thus the cross-validated score will go down because the data set the model will learn the exact training set without trying to generalize. So we need to adjust this constraint on the freedom of the model to balance the bias and the variance. When the model is underfitting, we give a lot of bias to the model, and it's not good because it's not able to capture the data. When we remove this bias, then the model is subject to the variance of the cross-validation split, and it will fit too much the training set and ignore the structure that is still there in the test set. So there is a lot of variance, and there is a lot of gap between the test score and the train score. Okay, so this is a profile that you can find with many different parameters in machine learning, with very different machine learning algorithms, but not always. So here we will do exactly the same, but instead of changing the value of gamma, we will change the value of C. And we will use the same kind of logarithmic scale for C. When we do this, so it's computing the stuff many times. So in your case, you might need to change an iteration over and over again here. We can do the same plot, but this time for C. And you can see that in this case, I fixed the value of gamma to a reasonably good value. And you can see that C can be, if C is too low, the model will be overfitting because both training and test score will be bad. But when you increase C, the model never overfits much because the value of gamma is such that the model cannot overfit much. So you can see that there is a dependency between the two parameters that makes it that way. So when we do parameter tuning of the models, we need to grid search the value of the combinations of all the parameters at the same time. So to do this, we can use the grid search CV utility of Scikit-learn. So this utility will take a grid of parameters to adjust and the range of values that they are authorized to move. So in this case, I use again a logarithmic spaced arrays for 4 values of C and 5 values of gamma. So it's starting from 0.1 to 100, and gamma is moving from 0.0001 to 1, because it's the logarithmic in the 10 base. So I can display this using pretty printing, and you can see the actual value. So here I just use 4 values for C and 5 for gamma. It would be better to increase those values to have a more fine-grained tuning of those parameters, but you will see that we will need to evaluate all the combinations of those 2 axes, and that will make many, many different combinations. So there is a trade-off between the time that we are allowed to spend on this and the quality of the tuning that we want to reach. So to make this not as costly, we will subsample the training set into a smaller training set with just 500 samples. And then we will run the grid search by passing the model and the grid of parameters that we are looking for, telling how many splits of cross-validation we will use to evaluate the test validation, the validation score of each individual parameter. Here I say that I will use all the CPUs of my machine, and then I will run the fit method on the dataset, on the small dataset. Here you can see that I'm using the IPython keyword %time to time the fit at the same time. It did not crash. Sometimes it crashes because of multiprocessing under OS6. Because it's using multiprocessing to fork several Python processes to make it run faster. So once I have fit my grid search here, I can access the best params attribute and the best score attribute and see which values of C and gamma in my grid were matching the best the data set. And we can see the test score in this case, which is 96%, 97%. We can also access additional information from this grid search CV object, because it also stores all the score values for all the points in the grid. So here I define 2 helper functions to parse those scores and rank them and display the best first. And then I will call this function on the grid scores attribute of the search object and display the top 20 first score. These kind of helper functions are not yet in Scikit-learn. We plan to improve the API to have this by default in the future. Yes?
When you're searching on the grid, you came up with C equals 1 and gamma equals
001.
0.001. That was one of the things you tried in the
Yes.
example of just changing C.
Yes.
And it didn't seem to be the most optimal when you did C equals.
In this grid search, I use a smaller data set. So when you use less samples, you are more prone to overfitting, and so you need more regularization to be optimal, because my data set is smaller. So the optimal value of C and gamma might change because the data set is smaller. So this is an interesting remark, and we will see later how to evaluate the dependency between the size of the data set and the optimal values for the parameters. So, yes?
Is the grid search deterministic?
Yes.
Is there a way to have a random search with a stopping threshold at a certain...
Exactly. So this grid search is exhaustive, so it takes very long time to compute. And furthermore, it's doing the computation in the order of the parameters that you provided. And sometimes some parameters are not important. So you could guess what are the good values of the important parameters much faster. So instead of using a deterministic grid search like we did here, we could use a randomized parameter search. And this is implemented in the master branch of Scikit-learn, but not yet in the stable version. So I didn't want to have you to install the master branch. So we just used the grid search in this tutorial, but it's implemented in master. So here we can see that those top values here They are either tied, exactly tied, or with an overlapping standard error here. So you can say that the C value here is not that important, but the gamma value here, which is always the same or almost always the same, there are two possible values here, is more important. So gamma is a more sensitive parameter in this case, and C, it just needs to be big enough, but it's not important how big it is. So I put some stars here to display which lines are overlapping with the first line according to the standard error. So to decrease the standard error, to be more precise, you could run more iterations of cross-validation, and that would decrease the standard error and be more precise. Okay, so once you've learned the object, by default it will refit an internal copy of the model using the whole data set, not a specific split, but the whole data set, and then you can apply it on the held out test data that we didn't use during the grid search for final model evaluation. And you can see that here the best model is actually performing better than expected. And why is it so? Is that when we computed the best model with the best parameter, we used the whole data set, so we had more data set than for the individual grid search splits. And so with more data, usually you get better models. So that's why the score here is a bit better. So I don't know if we have time. I think we will skip this exercise and move on to the next chapters, because otherwise we won't have time to see the interesting parallel stuff. So there are the solutions for the exercise. So if you want to experiment with model fitting, model selection for decision trees and ensembles of decision trees here, there is a good exercise with completely commented solutions on what you should expect and remarks. If we have time, we will come back to the exercise later. So finally, the last way to evaluate the bias variance trade-off in machine learning is to plot the learning curves. If you attended the tutorial by Jack this morning, you've seen one way to do it. Here we will do it again in a slightly different way. So plotting the learning curves is basically running cross-validations for different size of the data set. So here we have a fixed parameter for the model. So we pick up a good parameter using, for instance, grid search. And then we will vary the size of the data set by subsampling the data set. So here the train sizes are 100, almost 200, almost 300, and up until 1,000 points. And I will compute the cross-validation score using 5 iterations of cross-validations for each size of the data set, and I will measure the train performance and the test performance. So to compute the learning curves, it's very easy. You can just use iterate of the different train size. You can use the shuffle split cross-validation generator that accepts, I will put iterations here, that accept the train size parameter as we've seen in the previous exercise. We fit the model with the fixed parameter here, and we compute the train score and the test score. So here I'm doing it in a for loop in Python sequentially. So it's fast enough to do this, but we could run these for loops in parallel instead, because it's completely embarrassingly parallel. So once I have my train score and test score, I will compute the mean of the train scores for all the values of the train size, and I will compute the confidence interval based on the standard error, assuming it's Gaussian, which is not the case, but everyone does it this way. So, and then plot it using matplotlib, using the fill between stuff, because it's more beautiful. And so here you can see that when you increase the training set, the mean test score is increasing always. Sometimes it's oscillating a bit, then you need to do more iteration of cross-validation. But you can see that the train score can oscillate a bit in the beginning because it's very sensitive to the size of the dataset. But at the end, it can decrease a bit. If at the beginning it's 100%, you can see that at the end, it's just 99% or something. But it's getting closer to the test score. So you can see that for this given parameter set, when you have few data, the model will be overfitting because there is a large gap between the train and the test score. But when we have more data, you have much less overfitting, and you have a bit of underfitting that is appearing here because the train score is no longer 100%. And this is sensitive to so this means that the values that you select here for gamma is not always the same, the best, depending on the size on the training set. So here for this value of gamma, I never underfit. I'm always able to perfectly memorize the data set. But you can see that the underfitting is bigger on average, even though it's decreasing over time. So plotting learning curves is another way to analyze how the model is working. So how to interpret the learning curves is mostly by having a look at the difference between the train and the test score. And if at the end of the plot you can see that the test score is getting flat, it means that if you collect more data by paying people on mechanical turks, for instance, you won't gain much better models anyway, so it's not worth wasting your money this way. So it's much better to plot this line before actually paying people to annotate data. So if you have a flat line at the end and if the model is underfitting, it means that you should switch to a more complex model to be able to better capture the structure of the data. If you have a lot of overfitting and few underfitting, then you should do the opposite and switch to a simpler model, or increasing the regularization parameters in support vector machines, for instance. So this is just a summary. You have the details here. Depending on the kind of models that for decision trees or support vector machines, there are specific tricks. And just a final note, when you do the grid search for the optimal parameter value, sometimes the grid search itself can overfit. So you should, before starting to do a grid search, you should reserve a bit of your data for the final model evaluation. And so when you do this additional split, you say that you have a development set and an evaluation set. You do the cross-validation, grid search and stuff all inside the development set. And once you have found the best optimal parameters that you can get according to your learning curves analysis and so on, then you can compute the final expected score on the test set. Otherwise, you might subestimate your error because you risk overfitting by doing the grid search procedure itself because it's a learning procedure itself, so it can overfit a bit too. If you have time-based data, for instance, if you collect your samples over time, it's better to do this final split based on a specific date and to learn on past data and to evaluate on the most recent data, and because sometimes the distribution will change a bit over time, and if you don't do this, you won't be able to detect this change of distribution over time, and you might badly evaluate the quality of your model on the most recent data. Okay, just one final note. In this example, I did not do any kind of pre-processing of the data, and this is bad. Yes?
Yeah.
Yeah.
So I just found it a little
Yeah, okay. So if your goal is to evaluate the quality of one specific model, if you are mixing recent data and old data into the training set and evaluating on recent and old data, you won't be able to detect a change of the quality between the cross-validation scores that you computed during the model development and the actual test data, because they will follow the same distribution because you shuffled everything before doing the split. If you do the split on the time base and there is an evolution in the distribution, then you will be able to compare the cross-validation score on the development set with the final evaluation of the test score on the recent data. And if the cross-validation score on the old data is different from the is better than than the one on the most recent data, then you will be able to detect that the distribution has shifted a bit. Is it more clear? It's just to be able to detect the shift. It's not, if you want to take it into account, then you should train you should weight your recent data more than the old one to have a model that is closer to the end and to a recent event. But to be able to detect the stuff, you need to do the split on a time-based criterion.
But then the final training on the after process,
yeah.
the final training does have to take that into account.
Yeah, if you want to have the best model, you should use all the data available to build the final model. If you want to put a model in production, most likely you want to use the recent data as well, because if you are getting money out of the quality of the model, you should use all the model. The final model should use all of the data anyway. But when you use all the data, you are no longer able to evaluate the quality of the model. So you just have an estimate of the quality of the final model by using the data from the past. Maybe I'm confusing a bit with them, but okay. So just a final remark. I did not do any kind of pre-processing on this data set, but when you are working with support vector machines, you should never feed the raw data as I did. You should use the standard scaler that will remove the mean and adjust the variance of the individual features to unit variance. And when you do this, if you use the default parameters, you get almost perfect quality by default without doing any kind of grid search. Because when you do this, the data fits much better the default assumptions of the support vector machines, the kernel support vector machines. So, but if I had done this, the grid search would have been less interesting. So, okay. So, what time should we break? The break is in 5 minutes? Okay. So let's move on to the next section. And we'll do the break in the middle. So the next section is how to do this model selection assessment more efficiently when you have more computing power. As you've seen previously, we could use the nJobs parameter to use multiprocessing by default in Scikit-learn. But this has a couple of limitations. Let me see if I speak about this later. I don't remember. Okay, I don't speak about this. So Jobly by default will use POSIX fork on POSIX system. And sometimes this will break the runtime environment. For instance, under OS X, the linear algebra routines, they don't like when you do a fork without an exec, and sometimes the system can crash because of this. It will break CUDA and other stuff. And furthermore, multiprocessing in Python is not only work on a single machine, is not able to distribute the computation on a cluster. And finally, there is another limitation. that I forgot about it. So this is why in this section we will try to use an alternative implementation of parallel computation, which is the IPython parallel package. We will also try to optimize the memory allocation, the memory usage of the parallel processing by using what we call memory mapping to share memory between different Python processes. Yes, that was the final limitation of joblib. It's very hard of multiprocessing. It's very hard to do memory mapping with multiprocessing because it's using pickling hard-coded. So we will optimize the memory usage using memory mapping. And using those two primitives, we will be able to implement parallel grid search for model selection. We won't have time to do, oops, sorry, the parallel learning curves. But I will show you how to distribute the computation on the EC2 cluster using a nice tool which is called Star Cluster that makes it possible to start many machines with everything installed by default to run IPython parallel on a cluster. To do those exercises locally without the internet connection, we will just use a local cluster on a single machine using IPython. But keep in mind that all of these can run on many more machines that we are going to do today. So the main motivation is that when you do grid search for 2 parameters, for instance, and you have 3 possible values for those two parameters, you will have to evaluate 9 different models, 9 combinations. And furthermore, as there is some variability because of the cross-validation split, you need to do several iterations of cross-validation for each of those 9 parameters. So you have, for instance, if you do 3 splits, 27 models to evaluate. And those 27 models, they are independent of one another, so you can run this in parallel. Also, the data set is almost the same each time. There are only 3 different versions of the data set for those 27 evaluations. So if you have a big machine with 32 CPUs, you could just load those 3 data sets in memory once and make it possible to share the data. Sorry. For those models only once. So this is why we want to use memory mapping too. So maybe we should do the break now and move on to the parallel stuff right after the break. So it's 20-minute breaks, I think, and there's some coffee. So IPython parallel. I'm assuming that not all of you did the IPython tutorial yesterday. How many of you did the tutorial? Nope. Okay. And how many of you have never used IPython in the past? IPython parallel in the past? Okay, so it's worth doing it again. So I won't go into details, but I will just give you an overview of the main building blocks of IPython for dealing with parallel computation. So what are some of the motivations of IPython parallel? Good stuff is that it provides support for single node multi-CPUs the same way as it does for multiple nodes, multiple machines, multi-CPUs. So when you run your stuff on your local laptop with 2 CPU, you can run exactly the same program on EC2 with 30 machines. It will just go faster most of the time. It provides interactive in-memory computing because you can leverage the notebook as the natural user interface, and it has specific integration between the two using magic cells, using the PX prefix. So we'll see how to use this. And you can also turn in any engine of IPython parallel into a kernel, IPython kernel, which means that you can plug a user interface on it and plug a debugger on any engine on your network by just using SSH and plugging a debugger there. So when you have very tricky debugging situations, this single feature makes it very much better than multiprocessing, for instance. Okay, so to get started with IPython parallel, we need to start a cluster. So to start a cluster, let's move back to the dashboard tab of IPython. And you, on the screen where you can see all the notebooks of the folder, there is a second tab which is called cluster. And you can see that there is a profile configured by default for the local cluster. And you can scroll on the left and start a cluster by putting 2 here and pressing start. I think by default it will just use the number of CPUs on your machine. So if you have 4 CPUs, you can use 4. If you have just 1 CPU, if you are running in a virtual machine or whatever, put 2 anyway. It will be twice as slow, but it will make it possible to see how it works when dealing with at least 2 machines, at least 2 CPUs. So when we do this, it actually starts 2 new Python processes and connects them back to the controller process, which is started by the notebook, using 0MQ for the communication between the processes. And it will ship Python objects or commands and so on, using some serialization format that is configurable. It can be JSON, it can be pickle, it can be message pack, and so on. Okay, so now we have our 2 processes running in the background. We can move back to the notebook about IPython parallel, and we can import the client class. The client class can be instantiated without parameter, and when you do this, it will introspect the local folder, local IPython folder, and look for a recent JSON file with the description of the cluster. If you want to connect to a specific cluster, you can pass a parameter here with a JSON configuration file for a specific cluster, like the SSH credentials to connect to a remote machine and so on. By default, it will just connect to the local cluster with the 2 engines. If I use the len function on the client, I will see the number of engines currently registered on the cluster. This number can change over time if you create new engines later, but we won't do this. So we can safely assume that it's always 2. So to use the client, we can either use the object programmatically and call methods on views and so on. But it's much easier to use IPython magics when you are in an interactive session to directly access the engines from the client. So once we have created one such instance, we can use this %px magics and run stuff in parallel. So when I do this at the beginning of a cell with twice the %sign, every single Python statement below in the same cell will be run in parallel on each engine of the cluster. And if it prints something on the standard output of the engine, it will be sent back to the notebook interface to be able to introspect what's happening on this process. So here I'm writing a small Python program using the standard library to know the PID of the process and the host name of the machine on the network. And I'm just printing this information on the standard output of the process. And we can see that we have 2 standard output lines, one for each engine. Each engine has a number. And you can see that they are running on different PIDs, but they are running on the same host. And this host is my laptop. I am a PC. Yes? Do you have a question? No? Jake. Okay. If you have a question specific to IPython parallel stuff, Min and Fernando here are able to help too. So here we have our 2 engines displaying their states and we get this information back into the notebook process this way. We can also use a single line parallel statement using a single % here and just prefix the line with this symbol. And it will create a new variable A with the value 1 in the main interactive namespace of the engine. And I can just print it later and see on the standard output of each engine the current value of those guys. I can then change the value. It will be remembered because it's living inside the running Python process. So we are just dealing with many instances of Python processes, and they have their own variables in parallel. So I can double the values of 1 and get 2. I can also run specific statements on specific machines, on specific engines, by passing the -- target equals either one specific number or a slice. Here I'm using -1, and it will take the last started engine. It's better to use -1 rather than 0, which would be the first one, because sometimes the first one crashes and you start new engines. So -1 is always valid, whereas 0 might have died. So this is why I'm using -1 here. And here I am executing this statement only on the engine number 1. So if I'm printing the value A again, you can see that this A on engine number 1 has doubled, whereas the value of A on the first engine hasn't changed. Okay? Do you have any questions on the PX notation? Okay. So the alternative way to run stuff on the cluster is to use the programmatic API. And this is the API that would like to use when you're writing a library that would use IPython cluster to run in parallel. Because when you're doing a library, those guys wouldn't work. They only work in the notebook or in IPython. So to do this, you can first create a first type of instance, which is called the direct view here. A direct view can be created by slicing the client. So if I slice using the universal slice, I will get a description of all the engines at once. So I get a direct view on engine 0 and 1. And I can access the current namespace of those engines as I would do with a Python dictionary. So here the variable A on those two engines can be updated by doing this. So when I do this, it will pickle this Python object on my notebook, send it over to each individual engines using 0MQ, and then unpickle it on the other side and update the namespace main on those engines. When I do the opposite and access the dictionary, the dictionary interface, I will get the list of values on all the engines of the direct view. Okay? So rather than just updating variables, I will compute something. So to compute something, I will define a function that takes 2 arguments and compute the sum. And I will pass this function as an argument to the apply method of the direct view. And I will pass it 2 additional arguments. When I do this, I get back an object, which is an asynchronous result, which is just a handle on the result of the computation. And this call is non-blocking, so it doesn't wait for the engines to actually compute anything to return. So that I can schedule many work and then fetch the results when they are ready later. To fetch the result, I can just call get, and I will get all the result of the application of this function on all the engines of the direct view. So in this case, it's a bit stupid because I'm always computing the same thing on each individual engine. So just to better understand what's actually happening when I'm doing this, when I'm calling apply here, the notebook process will introspect this function, will introspect the bytecode of this function, will pickle it, will ship it over the network to the engines, will pickle the arguments those two arguments and ship them to the engines. The engines will call the function on the arguments. The result will be pickled and sent back to the 0MQ channel to the original caller. And once the results are available, I can call get and get a copy locally. Yes?
Minor comment for convenience. Often that's the result that you want to use in computations. .r is a property that is the result and does the same thing as the
Yeah, okay.
code and convenience option.
.r here. So it's, but when you are doing this, you are not just accessing an attribute, you are actually doing something, you are blocking and waiting for the result. So that's why I prefer get. Because you are actually telling the controller that you are waiting for the result, and it will block the client until the results are ready.
What's called if one particular host was bogged down?
Yes.
All the results were available from the rest of them except for that one, and you call it
Yeah, it will block. So if you want to, to detect this situation, it's possible, but I don't know how to do it quickly, so I won't answer this question. But most of the time, for our machine learning stuff, we won't use the direct view. We will use the load balance view that we will see later, and it's more resilient to this kind of failure. So I don't have the problem in practice because I don't use this. Let's see another example. So here I define a function that will import the socket module from the standard library and fetch the host name of the machine where it is running. And I will just apply this. When I do this, so I get my asynchronous result, and then I can get the host. When I do this, I can, instead of calling get, I can call get dict, and then I will have a dictionary that is keyed by the engine numbers, so that it's a good way to find which engine is running on which host in the cluster. So this trick can be used by using a dictionary comprehension here to fetch only one engine per host. So the last of the engines for each individual host. And this way I can compute a new direct view that will just have one engine per host. And with this direct view, I can, for instance, do stuff like installing Debian packages and stuff that will not support to have several processing doing the same stuff on the same host at the same time, or downloading data from the internet to be shared on the host. So this kind of direct view can make it possible to automate administration tasks this way. Yes, so here I get one engine by host. If I call values on this on this dictionary, I get the actual list of integers. If I pass this list of integers to this guy here, I can actually run shell command. Instead of using SSH, you can directly run shell command on your cluster directly from the notebook this way. You could also use SSH, but it's an alternative way to do the same. Just a note on the imports. You could see that in the previous examples, I did all the imports of the modules that I need inside the definition of the function, because when I will call this using apply, the definition of the function will be shipped to the network, but the dependencies, the module, the scope of the namespace might not exist on the target engines in the target namespaces. So it's a good practice to make your code more resilient when you have an individual function to run in parallel to do the import inside. Alternatively, you could use this notation, this context manager, to trigger import on the complete cluster, but there is a limitation. It does not support this kind of notation. So I prefer to use the nested import in the body of the functions. Okay, so let's do an exercise. So if you have the PSUtil module, you can write a function to introspect the process. Maybe I will just show you the exercise because we don't have much time. But this is interesting to show you how to introspect the memory state of the cluster. So the PSUtil module makes it possible to get a Python object that describes a running process identified by a PID. And in particular, there is this method, getMemoryInfo.RSS, that gives you the number of bytes that is redundant in memory on this process. So here I will do an example where I will write a function that takes a client as an argument and will define another function nested that will be run in parallel and will collect the memory in megabytes used by the process, the IPython process of the engine. So I just apply this on all the engines of my cluster and fetch the result using getDict and call this. And now you can see that the first Python process on engine 0 is using 30 megabytes of memory, and it's the same for the other one. So 30 megabytes is the default size of Python process with a couple of modules imported. I can have the total memory usage of my engines by just running the sum on the values and so on. Here I will allocate an numpy array with 10 million zeros, integers 64 bits. And so it's allocating on each engine 80 megabytes. And I can check that the memory usage of my cluster has increased by 80 megabytes using my previously defined function. So it's very nice to combine the two to debug what is wrong with the memory. There are other memory debuggers that are even better, but PSUtil is a good baseline. Okay, so this was the direct view. The alternative way to run stuff in parallel on a cluster is to use the load balanced view. The load balanced view can be accessed using this function on the client. So I call it LV. And I will run in parallel a function that computes the square of a value, but sleep a bit in the middle for 2 seconds to see the results before returning the results. So here I will apply this function on the input variable, input value 4. So it will just return 16. Oops, I forgot to execute those. So now I get an asynchronous result exactly as previously. I was too slow, so I will do it again. By default, it's false here when you call ready. But if I re-execute this guy later, it's ready true. And I can get the result and wait if it's not there, and I get a 16. So the difference with the direct view here is that I get a single response. So it just executed this low square function once on one of the engine. And the engine that was picked up was done according to some kind of scheduler using a load balancing mechanism to send the computation to different engine on the cluster when you call apply over and over again, so that it will spread the load on the complete cluster instead of sending the computation always on the same machine. Instead of apply, you can also call map with a function and a list, and it will spread this list over the cluster and maintain a task queue of execution in the result. So this task queue is the async map result. You can ask for whether all of the computation has been done or the progress. So 4 out of 4 are finished. And you can then iterate over the task queue to access the results. When you do the iteration, it does the get automatically, and it will block up until it's ready. So this load balancer mechanism is very nice, typically to implement embarrassingly parallel stuff like cross-validation and grid search in Scikit-learn. So when we do cross-validation and machine learning training in general in Scikit-learn, and we want to run, for instance, to train twice the same model but with different parameter values on the same data set, on the same machine, you want to have the two Python process share the same data set in memory instead of loading it twice. Because if you have multi-gigabytes data set, you will exhaust your laptop memory pretty quickly. So to do this, we can use what we call memory mapping to share memory between processes. So let's create, I will restart the cluster to clean up the memory. So it's not this one. Yes, this one. So I stop here and I start again. I wait a bit for the engines to start. And if I do this and I do len of client, I should have my two new Python processes. I will import NumPy in parallel on all individual engines. And on the first engine, I will create, yes?
One comment regarding a very common problem
Yeah.
when you stop and start a cluster is that you quickly switch to that tab and run the client and then connect them.
Yeah.
You may get an error because the engines are not up yet.
Yeah.
Just wait a couple seconds and run it again.
Yeah.
When the engines are just coming up, don't freak out. It's simply that the connections are not
Yeah.
up yet. So just wait a couple seconds, try it again, and once that cell executes cleanly, you know all the connections are wiped out.
Yeah. So if you want to you re-execute, you just hold Control Enter again on this guy, and it should work. You should be able to see the number of engines connected to the client. So let me just make sure that NumPy is imported everywhere. So on the last engine of my cluster, I will create a NumPy memory map. So this guy here is just cleanup code because under Windows, it's Windows, okay? And do not run this cell twice under Windows because otherwise you will have to stop the engines and start again, and there is no way around. Okay, ignore this if you are not under Windows and just focus on the memmap. So memmap is a way to build a NumPy array that will be backed by a file system file with the same size on the hard drive. And this file will be loaded in memory by the OS, the operating system, and made available to any process who has access to the file on the hard drive based on the permissions. And depending on the flag of the mode here, you can access it different ways. So when I create a memmap on this file, small memmap with a shape of 10 elements with dtype float 32 bits, with the mode write plus, it will create the file here on the hard drive. And if it already exists, it will zero it down. It will replace it by a new version, a new array with zeros everywhere. So be careful when you're using mode W plus, because you can destroy your data if it was your thesis data or whatever. Okay, so when you print this, you can see that it's just it looks like a regular NumPy array, but the memory is shared. So I did start my notebook by going into the solutions folder or the notebook folder. So when I do ls, it's running in the same folder here. And you can see that it's 40 bytes. And 40 bytes, it's 4 bytes or 32 bits times 10 items. So it's exactly the size that I was expecting. So now that I have created this file on the file system, I can run this in parallel on all the engines. And this time I will create a new array, but this time in read-write mode. And this will make it read the existing data, access it in write mode if you need to, but it will not zero it by opening it. So now you can see that in parallel you have access to the same array. So if on the last engine I change the value of the first element, so it will be a 42 here, I can print on the last engine the write mode array and the read mode array, and they have been changed, both of them, because they are pointing to the same memory segment, same shared memory segment. And furthermore, if I run this on the two engines, I can see that they have access to the same memory chunk. So they are actually sharing the memory, and you can write and pass data from one array to another this way. But be careful if you want to write stuff concurrently between engines, because you don't have any lock here. And so you might corrupt the data by writing half of a byte, half of a float concurrently. So make sure that you know that your engine are writing collaboratively by writing not at the same position. But we don't care about writing for scikit-learn, because we just want to read the read-only input data set this way and don't really care about writing yet. Yes?
Is it safe to write collaboratively as long as the positions don't overlap?
Yes. Yes. At least I don't see any reason why it wouldn't be, but yeah. Yeah. Yes? Larger arrays. By default, if you don't pass, no. By default, you pass it the file system, the file where you want to store the stuff. So you need to have a hard drive that is as big as the shape of your array, because it will actually write zeros on the hard drive the first time. And then it will just load in memory what is really necessary by the program accessing it. So it will just page data in memory. For instance, if you do a scan of the data, like you compute the sum of all the items, so it's a sequential scan over the data, it will page stuff from the hard drive into memory. And then once the memory is exhausted, the operating system will start to garbage collect automatically stuff that is no longer necessary. But when you start to do this, it can get slow because the garbage collection stuff is not always optimal. Yes?
Does it work with PyData?
I don't know actually, but that would be very interesting if PyTables would make it possible to memory map some of the tables. Yeah. But PyTables is using compression by default, so I don't think it's that interesting to memory map because you have to uncompress the stuff. But it's using compression that is very fast, so for sequential scans, for instance, I think PyTables will be much faster than memory mapping. But if you need to do several scans on the same data, memory mapping between several processes will be more efficient. So there are trade-offs everywhere. Okay, so now we can update the view, another stuff from another engine, and see that it's been propagated everywhere because it's the same memory. So memory map, you can use the same NumPy API on memory map as you would do on a regular array. So you can compute the sum, the mean, the standard deviation of stuff like this. And you can also we can also use psutil to check the impact of memory mapping. So I will define my previous utility functions to check the status of the memory usage of the engines. So up until now, I used very small memory map arrays, so they are too small to be visible here. So I just have my 31 megabytes per engine, and I have 4 gigabytes of free memory on my host right now. So on this engine, the last engine, I will create a big memory map of 80 megabytes, I think. So when I do this, I have yes, 80 megabytes. It depends on megabits, no, megabytes and stuff. Okay, so 80 megabytes. You can see that this has decreased a bit. No, actually, it hasn't decreased. It hasn't changed at all, because up until now, it has just written something on the hard drive, and it's not loaded in memory yet, because we didn't access the actual value from the Python program. I can open a read-only mode access to this file on all the individual engines. And here I use the time magic. And you can see that this is very, very fast because it didn't actually load the data. It just opened the file descriptor and tell the operating system that it might want to use this data at some point in the future. When I have a look here, I am actually printing the data, so I will access the data when I do this px big map. So I'm reading the data. I can see that now, no, it's almost the same. I don't know why. Maybe empty. Okay, let's go on. So no data has been loaded yet. I don't know how it's possible. Okay. By doing this sum, okay, I know. It's because when I do the print here, I'm just reading the first bytes and the last bytes, and I'm just ignoring the middle. The print function of NumPy is very smart. It doesn't load the data that is not necessary for printing. So to make sure that I'm actually reading the data from the hard drive, I will compute the sum of all the zeros on the first engine only. And when I do this, I can see that on the first engine, on the last engine, I mean, the memory usage of the last engine has increased, and the memory usage of the free memory of my host has decreased. If I do the sum in parallel on all the engines, I can see that it's much faster. It's just a couple of milliseconds, because the data has already been loaded in memory by this slow access. So now it's using the shared memory that is already there in engine number 1 automatically. So now it seems, according to the operating system, that my 2 engines have loaded the memory, but I can see that the free memory has not decreased much. It has decreased a bit, but not less than the actual stuff, because it's actually sharing the memory between the engines. Okay, so that's it for memory mapping. But instead of using memory map, the memory map API manually from NumPy, we can use the helper functions from joblib that makes it possible to dump any kind of data structure on the file system and then open it in memory map mode automatically. So if I write a class that has NumPy array inside, I can write this class on the hard drive by using the dump method of joblib here, and it will generate several files on the file system for each individual NumPy arrays that are inside this data structure. So it can be a complex data structure. It will create several files on the file system. And when I use joblib load on this pickle, any NumPy array inside will be memory mapped automatically. So instead, I get memory map instead of arrays. So by using this joblib dump and joblib load with the memory map mode enabled, I can dump the data set and load it in memory map mode. So this is exactly what I will do with this function here, that will compute cross-validation folds for a data set for machine learning. So we are back to our original topic. So we want to do cross-validation or grid search by sharing the memory of the original data set. So we will compute the cross-validation splits in advance and save it on the hard drive. And then on all the engines, we will memory map those splits once and for all and share them between them. So I'm doing exactly the same kind of stuff as we did previously, using a for loop on a CV object. But instead of computing stuff with those CVs, I will just put them in a tuple, a Python tuple, and save those tuples under a specific name on the hard drive. So let's do this on the digits dataset. When I'm calling this function on the digits dataset, you can see all those pickled tuples here. And if you run the ls, you will also see, you might need under Windows, I think I forgot this guy. Under Windows, you might need this guy, the exclamation mark. You can see that not only I have my pickle definition of my tuples, but I also have the NumPy arrays for the actual data stored as separate files that are memory mappable. Okay, so when I do this, I can load one of the specific CV cross-validation splits using joblib in memory map mode this way. And I will access one of the cross-validation folds in shared memory. Here I'm doing it in the notebook process. I'm not running it inside an engine process. But this is already working there, and it will work the same way for the engines. So once we have this, we can rewrite the grid search utility of scikit-learn. But instead of passing the NumPy array as argument, we will pass the file names of the CV splits, the cross-validation splits. And we will let the engines load the data in shared memory and compute their model and output the score. So we define a grid for grid search, exactly as we did previously. But instead of using grid search CV, we will have to build our own grid search CV implementation. So we can reuse this building block, iterGrid, which is an iterator that takes a grid as an argument and will output all the possible combinations of those parameters. So for each of these individual combination, I will train a model on a specific CV split and output the test score. So this is exactly what this Python function here is doing. So you can notice that the import of joblib is done inside the function because this will be run in parallel. So I'm loading one of the CV split file name that has been provided as an argument. Once I have access to the memory mapped dataset, I will update the model parameters with one of the elements of the grid that is provided in argument into a copy of my model, then fit the model here, and compute the validation score on the validation set. I don't compute the training set to make the steps simpler. I'm just training the model on the training set and computing the score on the test set, on the validation set. So I just define this function. So this function is not executed yet. To execute it in parallel on the cluster, I need some kind of orchestrator. And this orchestrator is this function, so grid search, that will take a load balanced view as an argument, the model that I want to optimize, the parameter grid, and the list of the CV splits that have been saved on the hard drive ahead of time. So to do this, I will iterate over all the combinations of the parameters. And for each of those combinations, I will output a bunch of IPython parallel tasks by calling the IPly method for each individual cross-validation split. So I will call this function, the compute evaluation function, on all the possible parameters and cross-validation split. So it's a nested for loop. But it's not blocking because I'm calling apply here, and that returns without waiting for the result. And I'm just storing the variable t here as a list of tasks, a list of running tasks. And those are asynchronous IPython results. So let's do this. I can try my function on this grid of parameters on the digits dataset that has been stored on the hard drive previously. So when I do this, it's scheduling the work. I can now monitor the progress of the computation by defining this function that will introspect the tasks that have been returned by the scheduler here. And for each task, it will compute the mean of the tasks that are ready versus the total number of tasks. So I can compute this function, and I was too slow to explain, and my process has already completed now. But if I rerun this faster, I can see that now I have only 4% of my process, 16%, and so on. So because of the asynchronous nature of the load balance view, I can actually run stuff in the notebook and watch it working, and I can even interrupt, abort the stuff by calling the abort method of the client if I want to stop before the end. So I can also introspect the results using this function that will find the best scores and output only the top 5 best scores. So, and execute this. And this function is taking the task as an argument. So all of them might not be ready. I'm just outputting the stuff that are ready by filtering here. So if I launch another sequence and execute quickly till the end, I can see that the progress here is not total, incomplete, but I can already access the score and see before the end of the computation that this guy is very good, and that if it's taking a lot of time, I don't need to wait until the end. I can stop before the end. And I did a trick here. No, actually, I did not do the trick yet. But there is a trick, is that instead of scheduling my work in the order of the grid, I can randomize the grid and do the same. And the parameters that are not important won't prevent the parameters that are important to be visible. So it's just an algorithmic trick, but when you do this, you can do randomized search basically, and not wait for the end to get the best result. So it might not be obvious explained like this, but if you want to know more about parameter optimization, randomized parameter optimization and search, you can read this paper by James Bergstra, who is also a Python developer, and he developed HyperOpt, which is another Python library that can work with Scikit-learn to do additional more advanced parameter search. So now we can move on to a more complete example by using a library. So I'm just defining a matplotlib stuff. I'm redefining a load balance view to make sure that it's working, a new model, a new support vector machine model, a new grid of the parameters gamma and c. And this time I will use this Python function here, model selection, this Python module. And it's actually implementing what I did previously, but with more advanced features. So here you can now see the validation score plus the standard error, the train score plus standard error, and the best element, and monitor the progress. So it's just a Python library that does exactly the same kind of stuff as we did previously, but with more features. And it also provides the ability to plot the score versus the different values of the parameters. So when it's running, so here it's completed, so I have 100%. But I can plot when it's running and see that the gamma value is very important. The model quality is very sensitive to the gamma value, so I should really not use a gamma value of 0.1 or 1, because I will always get into the underfitting regime. Whereas the C value is not that sensitive. Depending on the gamma value, the optimal C value is not the same, but it's not as important. There is no bad C value a priori. So I can do this again just to display the plot when it's running. So by default, if you do it too early, you have an empty plot. But if you can plot it again and see the partially aggregated values of your grid search coming here. Okay, so here I'm using 10 CV splits, so it takes a bit of time because I'm cross-validating 2 parameters, but it's still doable on my laptop. So I just have 100 of iteration on a small data set. But what I can do if it's taking too much time is to use a much larger cluster instead of my laptop. So we move on to this next. Just before moving to the cluster stuff, when you get this kind of profile here, you might want to zoom on this area to find the optimal value of gamma and discard those 2 guys and this guy. So I want between 0, 0, 1 and 0, 1. So I can change the value of my grid here, 0, 1. And I will zoom on this area and start again. When I do this, I can see I need to wait a bit to have enough samples. I made a mistake. Sorry. Oh yeah, it's I think it's this. Still not the right region, but yeah, it's getting better. Okay, I could zoom a bit more in the right region. So. Tick, tick. Oh, I forgot to abort the previous computation, so it needs to wait for the previous stuff, but it's good enough. Okay. So now I can see that I am only grid searching for values of gammas that are good, and now I can see the impact of C, and I can see that there are good values of C because I'm in a good region for gamma, and I can also display the training score in the plots and see the difference between the test and the train. So here I can see that the train is much better than the test, so it's overfitting a bit, but here it's not overfitting anymore. Okay. All right, that's it. So with this kind of tool, you can really finally analyze the computation, the quality of your model, but to make it practical in real life, you need to work with larger data sets and larger number of hyperparameters, and it would be too slow to run on a single machine, so we can use a cloud cluster instead to parallelize the work. So the most well-known cloud infrastructure is Amazon EC2, and it's one of the best because it's the most innovating and advanced, but it's also very good because it provides spot instances that allows you to rent cheap machines that can be disconnected at any times. But when you are just doing like exploratory data analytics, you don't care if one of your servers goes down. It's not as important as a transactional database with financial transactions. So you can get a much reduced cost by using spot instances on EC2. And to automate the provisioning of a cluster on EC2, you can use a star cluster. So star cluster is another Python project. So if you go on the web, you can find the documentation. It's developed by the MIT. And okay, it's a bit slow. Okay, so you will find the homepage if you need to read the documentation. Yeah, okay. So star cluster needs to have access to your EC2 credentials. So we won't do this right now, but I'll just show you how it works. And you have all the configuration if you want to try this at home later. So you will need your EC2 credentials. So you need a credit card to get those because you need to pay for what you use. And So you can put those two environment variables with your EC2 credentials and then install pip install star cluster. For this demo, we will need the master branch of star cluster because we will actually need the latest version of some of the plugins. So you can install the master branch of star cluster using this pip command, for instance. The first time that you run star cluster, it will you can run the help command and it will complain that there is no configuration file in this folder, and it will give you the choice, the option to create one with a template. So you can create one with a template and save it back somewhere and have the canonical example configuration file with all the inline documentation of all the individual options. So it's very good to learn how it works. For our use case, we will just use a simpler version. We will just use this file, this text here. You can put it in this configuration file. And before, you can just generate one SSH key without any kind of password that will be dedicated to connect to your star cluster machines. So the key you generate here, you need to use the same name here and in the configuration file. In the configuration file, you have a couple of global parameters, the key, and then what is very interesting for IPython is the configuration of the IP cluster plugin. So this plugin makes it possible to start IPython on each node of the cluster and register as many engines as there are CPUs on the nodes. You can also start the notebook automatically on the master node and provide a password to protect the access to the IPython session. There are also additional plugins here to stop the cluster and restart it. This restart plugin will only restart the engines. It will kill everything and restart the engines. So it's very good, for instance, when you're dealing with a compiled extension, libsvm or something like this, and you put bad numbers and you cannot control C into it because it's C++ code and it doesn't have any callback. So you can just kill it with this extension and then restart. There is another plugin that is interesting, is the Py package installer that makes it possible to install Scikit-learn, for instance, and PSUtil to run the examples that we've seen previously. Finally, there is the configuration of the cluster template. So a cluster template needs to know to have an SSH key, the name of a user, a Unix user that will be created on the machines, which shell and the size of the cluster. By default, you can put 1 to be sure, to be safe. And then the name of the AMI, so the operating system virtual image that will be loaded on each individual node. The kind of nodes that you want. For instance, if you use C1 X large, you will get 8 CPUs per node with 8 gigabytes of RAM. There are bigger nodes. They are more expensive too, and they are not available everywhere. So depending on the region that you choose, you might need to select lower machines. You can also disable SGE to make it faster, and you can configure the plugins that you want to start at startup. So in this case, we want to install Scikit-learn and PSUtil, and then we want to start IPython. So when you have this configuration file set up, you can run this command, star cluster start, pass the name of the template, the number of nodes you want in your cluster, so the master plus additional nodes, and a bid price. The bid price is a number of dollars that you are willing to pay per hour for having one machine running. You can ask for the spot history of the prices. Usually for this kind of machines, on average, it's less than 20 cents for an hour, but you can bid a bit higher to make sure that it doesn't get disconnected whenever the price moves a bit. And then when you do this, it will start and display a long, let me find one. Nope. Yeah, you typically get this kind of screen when you start. It will provision the AMI. It will start the new nodes, and on each individual node, it will set up NFS to share the home folder so that you can share the configuration files and data files and so on. And it will open some ports on the EC2 firewall to connect the IPython cluster, to connect to the IPython cluster. It will start the master node, it will start the controller, it will start the engines on each individual node, and it will connect them together automatically. And once you have this, it will give you a sample JSON file that you can use locally from your own Python process locally to connect to this cluster. But alternatively, you can also use this URL here to connect to the notebook directly and have the notebook interface directly hosted on EC2. So it takes 8 minutes to provision Spot instances. Spot instances is a bit slower than on-demand instances, but it's much cheaper, so it's worth waiting 8 minutes, I guess. Once you have this, you can go. Oops, model selection. In the notebook. So here I'm connected on EC2. Just wanting to check that this is the one that. Yeah. So this is a sample notebook that I've loaded on EC2. I can run it, and here you can see. Hopefully it will connect. That when I do len here, I have 22 engines instead of 2. So it's different. When I call a print statement, I get 22 answers. When I call where am I to get the PID and okay, let me move on a bit. Okay, here I can see the names of the machines and the PIDs of the processes on all the engines of the cluster. So here I have 3 machines: master, node 1, and node 2, and as many engines as there are CPUs. Minus 2 on the master to make it faster to connect to the engine and not to block the communication because the master is overwhelmed. Okay, so I will move on to the end. So here I am using the same kind of utility method that I presented to you earlier to split the digits dataset. I will make it this a bit bigger. To split the digits dataset and to memory load it. So I have a utility function to warm up the cache on each individual node of the cluster. Then I will define a grid search grid and launch the search. Oops. LB view, I forgot to execute. I forgot to execute those cells. Okay, so now if I run this, it was very fast. It's already completed because there is only 60 elements in the grid and there are 20 nodes in the cluster, so it just needs to compute 2 models per node. So it's very fast, so I don't even have the time to display anything. So I will move on to another model, which is more complicated than this simple model. It's using a pipeline, actually. It's a pipeline that will combine a feature extraction layer plus a linear model. And the feature extraction layer has 2 parameters, and the classifier itself has one parameter. And I will try 3 value for the first one, 5 value for the second one, and 5 for the last one. So it's 3 times 25 combinations. I think it's 750 combinations. And run the grid search. So I can monitor the progress here. And you can see after 3% of the process, I am already reaching quite good accuracy for this guy. And I can plot the parameters here while it's running. So I can see that this gamma parameter is very important, and this C parameter is not that important. It looks like the support vector machines that we did locally, because basically it's an approximation of it. And so now it's much, much faster, because it's still slow because I have so many combinations to try, but I have already reached quite a good accuracy with only 20% of the computation. Okay, so I can stop the computation here if I'm happy by aborting the remaining tasks, and it will stop the progress here. It should not, yeah, 1, 2, and I think now it should be done. Okay. So I think that's it for the demo of star clusters. So, but really the two together are working really good. So I encourage you to have a look at star cluster and IPython parallel together. They make a big difference. Okay, so let's move back to the tutorial. I don't remember how much time do I have left. 25 minutes, okay. And move on to text classification. So I will close this guy. Okay. So here on the dashboard view of the notebook, I can shut down the previous Python processes to free the memory. And now I will open the number 3, text feature extraction for classification and clustering. We won't have time to do any kind of clustering. We'll focus on classification, but the feature extraction that we will do here can be also used for clustering or any kind of unsupervised model analysis of text data. So let's execute the first cell to configure matplotlib, and then see the outline of this section. So many times when you're doing machine learning, you are dealing with data that is not as structured as you might expect, as you might want. For Scikit-learn to work, you need to express your data in a way that is a numerical matrix of 2 dimensions, the number of samples and the number of features. So to extract those numerical features out of unstructured data, such as a video or a bunch of text, there are clever ways to do it, and you cannot guess in advance. So in this section, we will focus on text data because it's ubiquitous. And it's good to know what are the building blocks to do feature extraction for text. But there are the same kind of domain-specific tricks also exist for audio data and visual data. So you need to read the literature on feature extraction on each of those specific tasks to know a bit more. So in Scikit-learn, we provide basic building blocks components for text data. A couple of stuff for very basic stuff for extracting patches from images or 3D volumes, but we don't provide feature extraction tools for any kind of domain. So if you want to do more advanced computer vision stuff, you should have a look at Scikit-image that provides image processing stuff, or even OpenCV and TippleTV and so on. So for text data, the basic feature encoding that we will use is called the bag of words representation. So this representation is very simple because it will just split the text by cutting the white spaces, for instance, identifying the individual words, and counting the word frequencies in each individual document, and ignore the ordering of the words. So you won't be able to detect the actual meaning of a specific syntax, of a specific sentence, by using this extraction, but it's good enough to be able to find the global topic of a document, because the distribution of the vocabulary of the words make it easy, make it good enough to detect the topic of a document, or to classify a document by topics. So to do this in Scikit-learn, we will extract the features and then feed them to a classifier. And to do this automatically, we will combine the two into a pipeline. And once we have this pipeline, we will be able to do model selection and model assessment, both on the feature extraction layer and on the classification layer at the same time, because we are able to combine those together. So, how to do text classification in 20 lines of Python. It fits on a screen. So we will import those utilities to first import a data set. So this data set must have been downloaded using the fetch data script previously. We will load a training set and a test set that has been previously splitted according to a specific date by the author of the training set, of the data set. Once we have those two data sets, we will feed them to a vectorizer object that will output a SciPy-sparse matrix numerical description of the text data that we will be able to feed to a scikit-learn classifier. In this case, I'm using a naive Bayes model, multinomial naive Bayes, which is very simple, but it's good enough for many classification, text classification tasks. And once we have this, we can also do the same exactly the same feature extraction on the test data to evaluate the quality of the model. So let me run this. So it takes some time because it's 20 megabytes of text data to process. And then it fits the model, and I have the scores, the training scores, and the test scores. So it's kind of good because in this case, I'm using 4 different categories. So 4 target categories. The data set is about news groups messages, about atheism, religion, computer graphics, and science in space. And so if I pick up a category at random, my score would be 25%. So here I get 85%, so it's not that bad for just a simple model. So here is a flow diagram that summarizes what we just did. We have a vectorizer object that is able to transform the text data into feature vectors, a SciPy-sparse matrix. I feed this SciPy-sparse matrix plus the labels, the identifiers of the categories, to a classifier. In this case, it was a naive Bayesian models. It will run the machine learning algorithm and output the statistical parameters for the fitted model. Once I have this, I can transform new data using the same vectorizer to get new feature vectors, compute the prediction using the predict method of the classifier, and get the most likely expected label for this new document. So we will go into detail about each individual steps. Under Windows, you might need to put the exclamation marks here. Not sure. So the dataset should have been fetched in the dataset folder. And in particular, there is the 20 newsgroup stuff. You can see that there are 2 subfolders, one for the training set and one for the test set. So in the training set, we have 20 categories, 20 subfolders, and in each of those subfolders, we have many documents, and they are stored in individual files with a dummy name. And those files are just simple text files. They just have the raw text that was posted on the newsgroup. So to load this in Scikit-learn, there is a function here which is called load files. I don't know if I have imported it before. That will use the structure of the folders to find the labels and load the strings of the files in memory. So it's only for small data sets, and we'll use the Latin 1 charset to decode the files into Unicode Python object. So I can do this. It takes a couple of seconds. So once this is done, I can access the target names attributes of this object, and I get the categories that were loaded. They are the folder names. If I access the target attribute, I get the integers labels for the individual messages in those folders. So for the first, actually it does a shuffling of the data set at the same time. But for the first document after the shuffling, I know that this is the 12 category. So if I count here to 12, it must be around here. So it may be scientific stuff. And I have this target integer label for each individual data. So in this training set, I have 11,000 documents. In the test set, I have almost 8,000 documents, a bit less. I can check that the data set is the data attribute is a list with the same number of items. And if I check the type of the first item of this list, it's a Unicode object. So I can display the content of items of my data set using this utility function. So I give it the index of the sample that I want to display, and I pass it the dataset object to be able to display the class name. So the first sample in my dataset is from the electronics news group, and you can see that there is some text that starts here. There is a bunch of headers, like mail headers, plus the body here. So it's the same syntax as the usual mail headers. There is just one tiny difference, is that the to header has been stripped off because it's the label, and it would be too easy to predict stuff using this label. But even those headers are kind of cheating because the actual body is just this. So we might want to strip this in the same way. So now I have the text, so I can have a look at another example. So here it's a mailing list, a news group for selling stuff. And I have the actual text, and it's a reply to another message. So I have the body of the other message also in this message. So I can introspect the size of my data set by assuming that this is an 8-bit encoding and just summing the number of characters. And you can see that once it's uncompressed and loaded in memory, it's quite big. It's 100 of megabytes. It's not that big, but it's not trivially small. So instead of using the big data set, the complete data set, I will just restrict to the 4 categories that I've seen previously, and they are stored in those 20 train small variable. So for the 4 categories that I've selected, atheism, religion, space, and computer graphics, I have just 30 megabytes and 20 of test. So now that I have my small data set, I will try this TF-IDF class from the feature extraction module in Python, in Scikit-learn. So if I create an instance of this class and print it, I can see the default values of all the parameters. And you can see that there are many, many ways to tweak the feature extraction of the text document. So by default, I would just set min_df to 1, which means that we won't cut off words that occur only once in the dataset. Depending on the version of Scikit-learn, this value is 2 or 1. So it can be confusing to switch from one to another, so it's better to fix it. And here I will just use 1 so that I don't cut any word from the data. So once I have my vectorizer instance, I can call the fit transform method on the list of text documents. So data here is the list of Unicode strings, and I will get the SciPy parse matrix. So it takes some time because it needs to parse the 20 megabytes. So it takes 3 seconds to count all the words in those 20 megabytes. And in the output, I get this matrix. So I had 2,000 documents. So this is the first dimension. And it counted 34,000 different words in my corpus. So each individual unique words will be mapped to a column in my matrix. And this way I get this sparse matrix. But you can see that there is a lot of zeros because the number of non-zero value is less than the product of the two. It's much less. So this format does not store in memory the zeros. It just skips them and just store the location of the non-zero elements. But apart from this, it looks a bit like a NumPy array because there is a shape attribute. So I can access the shape of the dataset the same way. So here the number of samples in my matrix is the same as the number of strings in my original list of documents. The number of features is the number of unique documents that was found in the corpus by the vectorizer. The vectorizer stores the list of words in an attribute which is called vocabulary, which is a dict. And if you have a look at the size of the dict, it's the same size as the number of features. So it's quite big, so I won't display it here because I don't want to crash the notebook. But so it's a big Python dict that is loaded in memory with the mapping between the feature names and the columns indices in the sparse matrix. I have the opposite mapping by calling this function, which will give you the names of the columns for the matrix. So exactly the same number of names. If I look at the first 10 names, I can see that I have dummy strings that are not very informative because they are digits. So I could tweak my vectorizer to get rid of those features because they are likely not very interesting. So I could tweak a regular expression to get rid of them. But I can have a look at the middle of the data set, of the feature names, and I can see that those are more regular words. They are ordered by alphabetic ordering by default. So when you have a data set like this in vector representation, one good habit is to use a randomized PCA to do a scatter plot of the different categories to know the structure, the visual structure of the data set. So here you can see that we have 4 categories, so 4 colors. If you remember the digits, we had very well separated blobs for the digits, even in 2 dimensions. For the text data, it's much less often the case. But we still have a nice separation between the red and blue and the 2 blues, the light blue and dark blue, and the green and red. There is kind of a line that separates the two. And you can see that the 2 blues, they are about atheism and religion, and they are overlapping because they share a lot of the same vocabulary. Whereas computer graphics and space are overlapping a bit, but not as previously, because they have more like a scientific vocabulary that can be shared between the 2 topics. So just by having a quick look using a PCA, you can check that the data is not completely noise. So the feature extraction did not destroy completely the data set. So now we know this. We can try to fit a text classifier. So before fitting the text classifier, I don't know, I've already displayed this before. So yeah, I just want to check that the X, which is the input, the 2-dimensional sparse matrix as input, has the same first dimension as the labels, because I want to have as many labels as I have rows in my matrix. If I don't have the same shape, the same first dimension, I will have an error from my classifier because it cannot know the labels for some of the rows. So once I have this, I can create a multinomial naive Bayesian object. This algorithm is nice because it has very few parameters. And actually, there is only one meaningful parameter, which is alpha. And the other, you can leave them to the default values. So I will just use the default value of alpha. No, actually, it's not the default value. I just use alpha equals 0.1 for now. But you should grid search this value to find the best one. And fit the data. So you can see that it's very fast. naive Bayesian is very simple. It's almost a linear model. So I can transform also the text, the test set, the test part of the data set. And once I have this new SciPy-sparse matrix plus the labels for this test data, I can compute the score of the classifier on the test data that was not used during the training set, during the training phase. So here we can see that we have almost 90% accuracy on a 4 category classification task. So it's the random level is 25%, so it's achieving 90%, so it's quite good. Just with bag of words plus naive Bayesian. I can also check the training score, and we can see that it's not underfitting much. It's almost perfect on the training set, but there is a gap between the two, a 10% gap between the two, so there is a bit of overfitting and not much underfitting. So we would need more complex models to, we wouldn't need more complex models to improve the quality. We just need to simplify the feature or better regularize the model to increase the performance. So to understand exactly what was done during the feature extraction phase, we can have a deeper look at the TF-IDF vectorizer. TF-IDF means term frequency inverse document frequency, because it's weighting the words that it sees in the corpus based on the frequencies of the word inside the specific document, but it's also measuring the frequencies of the word across different documents, and the words that are very common have a weight that is a bit decreased to make them less important because they are less discriminative. So to understand the meaning of all the individual parameters, you can have a look at the docstring of the constructor, and you can see that it's quite well documented, so you have an explanation for all of them, and you should be able, by reading this, to understand what kind of tricks you can try. The best way to introspect what is actually done by the vectorizer is to call this method build analyzer that will take those parameters and generate a Python callable that will transform a string into a list of tokens. So if I run this on this string, I love Scikit-learn. This is a cool Python lib with some punctuation and capital case and so on. I will get only lowercase words. The ordering is the same here, but it's not necessarily the same because the ordering does not matter in the bag of word representation. You can see that the I has been discarded, that Scikit-learn has been splitted into 2 words. The punctuation has been removed, and the capital case has been transformed to lowercase. So we could customize this way of transforming the data by passing a custom preprocessor and a custom regular expression. So this preprocessor does not do the lowercase. It's just returning the identity function. And this regular expression here is treating the hyphen word, the hyphen symbol as a regular word, as a regular character, and so is extracting words without splitting on the hyphen. So I can try this again, and now I can see that I have capital case, and also I consider single letter words. Yes. So I have the I and so on. So you can customize the way the feature extraction is done by tweaking those parameters. So now there is an exercise. So I will ask you to write a preprocessor callable that will remove the headers of the functions. I don't know how much time. I think, yeah, we won't have time to do the exercise, so I will just show you the answers. So how much time? 5 minutes or less? 1 minute, okay. So just see. What was it supposed to? Okay. 1 minute. So this function is a function that strips the headers by identifying two blank lines, two consecutive blank lines, and it will just return the body in lowercase. So if I apply this to some text document with the header here, I can apply it here and I get only the body. When I pass it to the vectorizer here, I pass my preprocessor here, and I compute the score of a model train on the output of this guy, I can see that now I get 82% accuracy instead of 90%. So it has been decreased a bit, but it was cheating before because the data set was giving information that you don't have access to in real life. So the real accuracy of the model is more like this. Okay, so I think we should stop here. So there are plenty of more material about text extraction and how to compute the performance metrics and the best parameters using grid search on a pipeline at the end of this notebook. And there is a last notebook that also explains how to scale text classification to larger programs, to a larger data set by using a different vectorizer, which is called the hashing vectorizer, that doesn't use a Python dict internally, that makes it possible to not have a state and thus to do online incremental learning and distributed learning because you don't have this vocabulary attribute that is so painful to handle on large data set. But if you understand how the TF IDF vectorizer works, the hashing vectorizer will work exactly the same way, but it's kind of an approximation that makes it more scalable, but on the other end, makes it less easy to debug what's going on because it's using a hash function instead of a vocabulary. Okay, so I think that's it for today. Thank you very much, and if you have questions, I can take them after the tutorial. It can also be a sentiment analysis when you are trying to see on social networks whether users speaking about a specific topic are speaking about it positively or negatively, to know who are the influencers on a specific brand, for instance, and identify people you should focus on converting to speaking positively about your product, for instance. So those are the kind of application of text classification. Then, if we have time, we will move to how to scale text classification to larger data sets. And if we are able to scale, we can do two kinds of things. The first one is how to do online learning or out-of-core learning, which means how to fit a model to a data set that doesn't fit in the main memory of a single computer. So how to stream the data into the model and to make it fit to learn incrementally and then have a final model that is a summary of a complete data set that doesn't fit in memory. And the second part will be how to do this in parallel on several machines, on several computers, possibly distributed on a cluster. So before diving into the actual tutorial, the organizers of PyCon are looking for volunteers. So tonight there will be a swag bagging session. So if you can help fill 10 bags, it's good. Otherwise, they need people for the registration desk. I think tomorrow morning will be very important. And so if you are interested in volunteering, you can go to the bit.ly/PyCon volunteering status page. And finally, there will also be, sorry, yep. If you go to the tutorial setup page, notebook, at the end there is a link for the tutorial survey. So it's a SurveyMonkey page. So if I forget to ask you to fill it at the end, please do it tomorrow or when you think about it in the coming days. All right, so everybody's fine with the setup? Okay, so let's open the first notebook, which is called Model Selection and Assessment. Actually, maybe before going into this one, let's get familiar with the notebook itself. So instead, click on the new notebook page here, and we will see how it works. So the notebook is kind of a shell where you can write both documentation and see the output of the execution of the code you put in line. So whenever you put some Python instruction, for instance, print something, here you can execute it by pressing Shift-Enter, and it will move to the next cell, and if it's the last cell, it will insert automatically a new code cell at the end. So in the notebook, you can define variable as a regular Python program, and then so welcome to this tutorial session. Now that the base setup is done, so the goal of this tutorial will be to introduce you with advanced machine learning concept as implemented in Scikit-learn, and we will especially focus on making basic machine learning algorithm from Scikit-learn scale to largish data set. It's not big data because we won't address like Google size data set, but stuff that might not fit in the memory trivially, or stuff that will need more than one machine to run. So during this tutorial, we will mostly use the laptops that we have here. So the data sets are even smaller than what you could do if you had more machines. So a couple of words about myself. So I'm Olivier Grisel. I'm a regular contributor to Scikit-learn. Jack, who is moving around, is another core contributor of Scikit-learn. So Scikit-learn is a library for machine learning that started a couple of years ago, and it's getting more interest because machine learning in general is getting more interesting. So myself, I'm interested in natural language processing, a bit of computer vision, predictive modeling in general. And I'm recently tried to investigate with how to leverage cloud computing resources to make all of those run better. And I will be starting my own machine learning consulting business. So if you are interested in a project, you can go to this webpage, orgrisel.com. So the outline of this tutorial will be the following. We will start with one of the most fundamental concepts of machine learning, at least one method that everybody should know about and apply on a day-to-day basis when dealing with machine learning issues, namely how to do proper model selection and assessment of the quality of the statistical models that we fit on the data. One of the motivation for dealing with this during this tutorial is that this specific kind of task that we do on a regular basis in machine learning are almost all of the time embarrassingly parallel, and so they are amenable to scaling on a computer cluster using IPython parallel. So we will have in the second section an introduction to IPython parallel and an application to the topic of the first section, which is model selection. Then we will have a break at some point. I don't know. It will be at 2:50, something like this. And then we will move on to text feature extraction and classification. So it's one of the main application areas of machine learning. It's how to process unstructured data such as text. And we will focus on classification, which is a simple task to illustrate the issue. So text classification, in real life, it can be like spam classification, fraud detection, or comment spam or mail spam and whatever. print the content of variable. It's just a Python process running in the background. When you go back here, you can change the existing code and re-execute this guy several times by pressing Control Enter, and in this case, it won't move to the next one. So this is very interesting to monitor the state of a process running in the background. So it's Control Enter. And you can see that the state of my notebook has changed because now my A variable is 13 here. You can also, if you are interested in tweaking something, you can copy and paste a cell by pressing Control M C, Control M V, and it will duplicate the cell, and you can actually put it somewhere else, Control M V here, and then you can edit it and change it. If you want to get rid of it, you can press Control M X or D to cut or delete.
You might want to show on the help menu.
Yeah, and then there is the okay. All of those operations you can perform them using the menu, and then you can get the list of the shortcuts by pressing Control M H for help. And here you have all of them.
Or from the help menu.
What?
Or from the help menu.
Help menu?
Help keyboard shortcut.
Oh yeah, I missed it. Okay. Okay, so the most important are the Shift Enter and Control Enter to either run in place or to move on to the next cell. Actually, it's the opposite. Okay, so now we can close this tab and go back to the first one, which is model selection and assessment. So in this first section, we will see different kinds of ways to evaluate the quality of machine learning model. And especially, we will try to detect one of the bad situations where we can end up when learning a machine learning algorithm, which is called overfitting. So overfitting is when a machine learning algorithm has learned by heart what is seen in the past and is not able to generalize to unseen data in the future. So this is a trap, and the best way to detect whether or not we are in this trap is to use what we call cross-validation. So we will see how to do this with cross-validation. Once we know how to do cross-validation, we can extend this to do hyperparameters tuning, which is how to automatically tweak the knobs of the machine learning model, like the hyperparameters, the constructor parameters of Scikit-learn models, by using what we call grid search, which is basically trying many different values for those parameters, learning the models on the data, and then validate it against new data and measure the performance and selecting the best model according to this cross-validation performance evaluation. Once we have this, we can also evaluate the quality of the model and especially try to see how we fit in the bias variance trade-off by plotting what we call learning curves. And finally, we will see that we should always do this on a specific subselection of the data set, which is called the development data, and try to get some held out data for the final evaluation at the end. So let's start. So before starting with the actual execution, we need to run this cell to configure the plots and import a couple of utilities. So please run it using Shift Enter, and then it will move the cursor to the next one. If you get an error message, raise your hand. Okay, so to illustrate those concepts, we will need a data set. So as we did this morning in Jake's session, we will use the digit dataset that comes by default in the Scikit-learn source code, so it's easy, you don't need to download anything. So to get this dataset, you can use the scikit-learn.datasets package and import the load digits function. When you import this guy, you have a digits object that has a description, so we can print it. And you can see that it's a dataset about optical character recognition, where all the characters in the dataset are digits from 0 to 9. And there are small images with 8 by 8 pixels. So if you put all those 8 by 8 pixels on a line, on a row in a matrix, you will have 64 pixels per image. And as we have 5,000 such images, we say that we have 5,620 samples and 64 features. So hopefully you're all familiar with this way of treating the data, this vocabulary. This is the standard vocabulary for machine learning in general and in scikit-learn in particular. So let's load the data set into two variables. So the first variable will be x, which will be a two-dimensional matrix with the actual pixel data. And y will be a one-dimensional variable with the integer labels for each of these pictures. So if we execute this, we can see that we can plot the shape attribute of the NumPy array x and the same for y. And we can see that the data shape is this, and the target is just one-dimensional with the same number of samples as the first dimension. So here you can see that we have only less than 2,000 of the pictures of the images because it's just a subset of the actual data set that is published on the internet. We can also use the NumPy function unique to get all the different values of the Y array. And we can see that there are 10 classes for the 10 digits, and those classes are represented by integers to be memory efficient. So we don't have strings in scikit-learn. Most of the time we directly process numeric values to avoid storing strings in memory to reduce the memory usage and make the computation faster, basically. So I could insert a new cell here and have a look at what's the content of the Y variable. And you can see that the data set has been a bit shuffled. I'm not sure, so I will move a bit in the middle. Actually, it hasn't been shuffled, so it's just a repetition of pictures from all those values. Concatenated one after the other. So the dimension of the data is called the samples for the first dimension and the features for the second dimension. So the samples are the pictures and the features in this case are the pixel values. Once we have this data set loaded in memory, we can also use matplotlib to plot the actual content. In this case, we know that those are pictures. So each individual row in the X matrix will be 64 pixels. So we can reshape it to a picture with 8 by 8 pixel and use the imshow function of matplotlib to display it. So if we do this, it will iterate over the first 5 samples in the data set. And it will display the true class in the title using the Y vector and use the imshow function to see the pixel value in a visual representation. So we used interpolation nearest here to disable the interpolation features of matplotlib to see the raw signal that we have in the dataset. So here we can see that this is a 5. It's quite obvious. A 0, a 6, another 0, and a couple of zeros actually. So once you have a data set loaded in memory, the first stuff that you could do when doing classification in scikit-learn is to try to represent the structure, the distribution of the data. And as we are human people, we try to see stuff in 2 or 3 dimensions. So we'll try to reduce the data into to project it into a 2-dimensional space, and then do a scatter plot into this space to see the actual distribution of the data. To do this, we can use randomized PCA, which is an approximate principal component analysis method that is provided by default in Scikit-learn, which is very scalable. So you should always use this one when you want to do visualization on large data sets. So we can import it from the decomposition package of Scikit-learn, and then run it by building an instance with the n components parameter set to 2, because we want to project the data into 2 dimensions, the first 2 principal components of the data. And then we will call the fit transform method on the data, and that will extract the structure of the data and then project it into this space at once. And the resulting variable will be xPCA,